This time, we'll tackle a graphics archive that takes more than a hex editor to understand. The PIC files proved to be more inconsistent than the SCR, Faces, or BLK files that we've already taken apart. We'll start with a hex editor, but we'll soon see that the rules for one file don't apply to the other files. We need to use a disassembler to show us how the game itself handles these files. I'll give a quick primer on disassembly with IDA-Pro before we jump into the application binary to find the information we need to build our extraction utility. Like always, we'll start by copying the PIC files to our workspace. Let's open the last file and take a look. Widen it to 32 bytes. Okay, so we see the usual signs of a 768 byte palette due to the section break here. No other header information. Now scrolling through, there's obvious signs of repeating sections spaced much further apart than the 32 bytes. This is a noisy but somewhat sparse file. Let's change the encoding to DOS to get a few more glyphs to pick from and hope we can find something that definitely repeats. Alright, let's try this. 320 bytes. That's something we'd expect since we know the game resolution is 320 by 200. Let's change our width. Well, we see something that looks coherent, but it's still tough to make out. I'd say we're onto something with this file though. But let's open another PIC file. We'll try number 13. Okay, this is not what we're looking for. The 320 width isn't right at all. Now that means all the PIC files aren't the same. Now if I open number 19, we can see another inconsistency. And this file doesn't even have a palette. Alright, so we have an interesting challenge here. We could continue on with the hex editor, open all 9 files to determine which ones have palettes, and then try out various sizes for resolutions. We could find about half of them if we tried the usual suspects, such as all the powers of 2 or multiples of the screen resolution size. But you might wonder if there's a better way to figure this out, or at least a more interesting way. And there is. So let's think about the problem for a minute. We know that each PIC file has a different resolution and may or may not have a palette. Now the application loads these files at some point, either on startup or on demand. Well, how does the application know how to process the files? It doesn't just know without being told what to do. Now, generally speaking, there's 3 ways. First, the file tells the application how to process it, usually through a header that contains file metadata. Well, we know that's out because the PIC files have no header. Neither have any of the files we've looked at. Now, second, the application indirectly identifies the processing steps by looking at the file extension or the size or the structure. Now, that's an outside possibility here because, well, it's unusual for an application to figure out its own archive by using more than just the file name. Now finally, there's the likely case that the application itself already knows the exact structure of each individual PIC file, and it's been hard-coded into the binary file. When the application needs file, say, number 20, it already knows the exact specifications. Now let's prove this right now. Now in PowerShell, let's go to the game installation directory. Now first we'll look at the PIC file we've already figured out. We know it comes with the usual 768 byte palette, and we figured out by hand that this is 320 pixels wide. So at 32,000 bytes with 1 byte per pixel, it must also be 100 pixels tall. Now it's probably a good idea to write down the hex equivalent of these resolutions. 320 decimal is 140 hex, 100 decimal is 64 hex, and while we're at it, we may as well include 300 hex since we know that the 768 byte palette is there. I'm betting we can find these exact hex files in our exe file. Now also note that the other PIC files vary widely in size, so they probably all have unique pixel resolutions. And we want to find those resolutions in the binary file. But first, we'll find the specifications for the td1-20.pic file that we've already figured out manually. But the next question is, which binary file do we look in? The game comes with 10 different binary files. We'll take a chance that the file name td1-20.pic is hard-coded as a string literal in one of the binaries. In Unix or Linux, we can grep for the string, but since I'm in Windows, we can use select string like this. And we have a hit. Our pick file appears one time in file0001.exe. Let's copy that file into our workspace so we can use the disassembler without cluttering up the game directory with temporary files. Now let's take a first look at the game binary with the free version of IDA Pro. Now I'm going to open the target file and keep the default processing settings. Now the first time you load a binary, it takes a while for it to parse the instructions, build the data tables, and resolve cross-references. While this loads, I'll share some comments about the process. For those of you who have no interest in assembly, feel free to jump ahead in the video. We're going to find the exact resolutions of all 9 PIC files and which ones have palettes. Now if there's any old school assembly artists watching, this should be a trip down memory lane. Traffic Department relies almost entirely on 16-bit instructions and registers. There's no dynamic linking, and all the code exists inside the standalone exe files. The only dependency is on the MS-DOS API to handle interrupt vectors directly from the file. No wrapping or other external libraries are involved. Now if you're casually familiar with assembly, then you'll find the style much like something you'd see in an old textbook. It's simple and archaic. Now my window is organized for maximum space. The top colored bar is the map of the file and its sections. Now the far left tab is the main interactive code tracing window, where we'll be spending most of our time. Next to it we have the hex view that follows the same position as the interactive view. It's just like a hex editor. Next is the export tab, which has a single entry point to the file. Remember, DOS is only single-threaded. Since there's no dynamic links, the import tab's empty. Now the names tab lists all of the aliases that IDA Pro generated during parsing. Now these are only within the disassembler program, and they reference memory addresses within the exe file. If we rename variables within the exe file, they show up here. Now the functions tabs show us all of the independent code blocks in the file. IDA automatically names them based on the code segment and address. A full reverse engineering project would be to go through all of the functions here, figure out what the code does, and rename the functions to something more useful. We'll do 3 or 4 of these out of the 350 during this video, and maybe a few more throughout the rest of the series. Now the string tab will be very useful to us since it contains all of the constant text data that we see in the game that isn't directly part of the graphics. We'll be here several times throughout the series to pull text. Now in fact, I see a low-hanging fruit, so I'll give you a quick example of chasing down the real name of a subroutine by following a string. Now if we click on the text here that says Mission 1, we jump to a point in the file where this text string is defined. We then have the option to follow it to where it's actually referenced in the code, so let's follow it there. Now you may remember that we see this Mission 1 string during gameplay when we start a new game. Well, now we find ourselves at the top of a large subroutine. The Mission 1 string is referenced right after the first branch. Now notice that the last comparison in the branch is between this byte value and the number 1. Now if they're the same, we go to Mission 1. But if the byte values are different, we follow a different branch. Let's follow it. And there's another jump, so let's keep going. Okay, now we compare the same byte value with the number 2. If it matches, we go to a code block that references the string for Mission 2. We're located right here in the function graph. So hopefully you can see that this particular byte value contains the actual value of the current mission the player is on. So let's rename this byte here to current mission, and we'll go back to the start. Notice that the byte reference has been renamed, so our custom name is everywhere it's used in the disassembled program. Now this entire structure on the map on the side here is like a large if, then, and else ladder, or switch statement that matches the current mission and drives the player through the game. And we also have a better idea of a good name for this entire subroutine. Right now IDA calls it sub 10F06. I think we should call it GameFlow Loop. That name now appears in the master function list, and filling out this list with real names like this is one part of a full reverse engineering project. Now, of course, we can do a lot of other things. Some would be obnoxious, like changing the jump address to send the player to the last mission in the game instead of the first. And also, we identify the byte that holds the current mission that we're on. So we've taken the first step in building a game trainer that we can use to modify the byte to jump to any mission at any time. This video is probably running long, so let's get back on track. We're here to find out how the td1-20.pic file works in the application. So we're on the lookout for how the binary specifies the PIC file resolution. We know from the hex editor that the palette is 300 hex length and the image is 140 hex wide and 64 hex tall. Let's find the PIC file name definition in the string tab. We'll follow it to its home in the code. Now, as with most string operations in assembly, we have a source and destination indexed registers pointing around it. Now, another subroutine is called here, and if I hover over it, I can see the header without having to click through to it. Now, in the header, I see more indexed register operations, and a change of direction operation, and a store operation. Now, these are all operations consistent with string manipulation, and this should be expected since the string has to be manipulated for an eventual syscall to open the file. Now, I'll call this subroutine parse string. Now, the next function call has an interesting header. It moved the hex value 3D into the upper byte of the accumulator. Now, I bet if we follow this routine, we'll see the syscall on interrupt 21 to open the PIC file. Alright, looks like we have to jump through twice. Okay, right here, the syscall interrupt 21 is invoked. Now, normally IDA would tell us what the syscall is, but it lost track of the 3D hex value since it was done in a different frame, or a subroutine. And we had to jump twice to get here, including after the AH value was set. Now, most people don't keep all these interrupt numbers in their minds, but fortunately an engineer named Ralph Brown spent decades of his life tracking system interrupts, and we can reference his work easily. Just type in Ralph Brown in Google and go to his HTML listing of system interrupts. Interrupt 21, scroll down to 3D, and here we see that in DOS, interrupt 21 with the upper byte set to 3D is a system call for opening a file. Now, while we're at it, notice that 3F is the syscall for reading a file. If we check out the details of the file opening syscall, we see how the interrupt has to be set up in the registers and the output. Notice that the accumulator value AX is set to the file handle that we need to access the file later in the program. Now, back in IDA, we can rename the byte used to store the file handle in AX with an appropriate name. And back in the main routine we were following, we can rename the whole function call to open file. Now, the next function call looks like it takes the file handler and compares it to 0. Let's take a closer look. Yes, if the handler is anything but 0, it goes back to what it was doing. But this is the classic error check to make sure that the file actually opened. If we follow the bad path, we can see it eventually just crashes out of the program. This is an error handling routine. Let's go back to the top and name the function that way. Now, down in the next code block, we see another unnamed call to a subroutine. This one has that 3F hex value that I said earlier might be the hex value for reading a file. However, it's not in AH, it's in BL. Let's follow it and see if it eventually falls to AH and invokes interrupt 21. Sure enough, so this function reads from the file. So now we have a familiar situation, except now we're looking at it in assembly code. Up here we open a file, we set the variable here to 1, and then we read from the file to check to see if that variable has a value of 300 hex, which is 768 in the decimal. If not, we increment the variable to read another byte. This is the application reading the palette from the PIC file, just like a for loop in C. So we've almost found the information we're looking for. And down here, we find something we are looking for, the 140 hex value, which is expected for a 320 pixel width of a row. Now, it actually gets compared here with one less than the value, which is 13F. This forms the inner loop, which reads a pixel in each row. Then we have an outer loop, which reads every row in the image. Now the comparison for the height is right here, the expected 64 hex, or 100 in decimal. This is the classic nested loop that we've been programming in C over the last couple of videos, except this is how the application does it in assembly. Now right here in the middle of all this is the function call that matters. Here is where all the bytes that are read are sent to the monitor. Now back when this game was made, applications had direct memory access to hardware devices. Now for more information, just Google search here the 3C4 DMA ports or 3CE DMA ports. Let's give this function the right name back in our main routine. Now just to wrap this up, let's look at this subroutine down here after we've read the entire image. Now we can see the purpose right here in the first couple of lines of the header. This is where the file is closed, so let's give it that name. Now we now know how the original game processes the PIC files, so let's fill in the blanks. Looking at the big picture on the side, we can see that we're at the tail end of a much larger routine. This is because we started out with the last PIC file in our archive. 3 other files get processed further up the chain, so let's work our way back and quickly point out the details. PIC file 13 reads in the palette. It's apparently hex value CA wide, which is 202, and 55 tall, which is 85. So it's 202 by 85. So next up we have file 14, which has a palette. It's C8 wide and C7 tall. So I'll just write that down as a squared off image. C8 is 200, so I'll just call the file 14 200 by 200. Now the width is more important than the height, since an incorrect height will chop off the row at the bottom, but an incorrect width will misalign the entire file. Now the final image in this frame is 96 by A9, which is 150 by 170. Now, which image file was this? I forgot to look at the name. Okay, number 16. Now let's find the missing files, which are 15, 17, and 19, and secret.pic. Alright, 15 has a palette, and it's FE or FF, which is by 78, which is 255 by 121. Now, number 17 is a bit unusual. It looks like there's no palette since there's no 300 hex. We can see it's 13F by 59. That's 320 by 90. Number 18 has a palette and is AA by 67. So that's 170 by 104. Odd looking function here. I don't see 19 anywhere, so maybe it's not used in the game at all. Okay, finally, Secret has a palette and is 140 by 1F. So it's wide and skinny. It's 320 by 32. Well, we made quite a few annotations in the file, so we'll save the database and quit out. IDA doesn't actually change the application file at all. It creates a separate database that it pulls from when we come back to the file later. Now we're ready to program this up. Let's get both the old make file and the default palette file in our working directory. Now I'll fix the case on this palette file, you never know. This time I'll rely on our first SCR file as a reference since we're back to dealing with only a single graphic per file. Let's save the new file as PIC to BMP. Better change up that make file before I forget. I'll add an appropriate description. And we can copy everything, including the main prototype. First, we have to get the image dimensions based on the file name input at the command line. Then we'll make the surface since we have the dimensions. Then we'll get the file size so we know how many bytes to read. We have to pull the palette data from either the PIC file itself or from the default palette file. Then we'll follow the same routine that we've always used to extract image data. Change the file name and save. Now, since most of our PIC files have an embedded palette, I want to start off by setting a Boolean variable to indicate that. Now we'll set the image dimensions based on the file name. I'll be using an ugly if-else ladder. Remember that string compare functions return 0 if there's a match, hence the not operator in front. Now I'll use short variable names since I'm one-lining each file name. Now secret was 320 by 32. 13 was 202 by 86. 14 was 200 by 200. 15 was 255 by 121. 16 was 150 by 170. 17 was 320 by 90, and it didn't have a palette. 18 was 170 by 104. Now 19 we didn't find in the file at all, so I'll set that to max possible size so we don't accidentally write beyond the surface. And finally 20 we found by hand, which was 320 by 100. Let's declare the new variables. I'm in C89, so there's no Boolean type. I'll just use an 8-bit int. Image dimensions are good for 16 bits. The surface creation doesn't change except for the dimension variables. We'll copy the declarations too. This says get file size, but I need to open it first. We'll make that change and then I'll have to retype the file size finder since the SCR model doesn't use it. We'll declare the file pointer and the 32-bit size variable. So the palette file pointer could be either the pic file itself or the default palette file that we haven't opened yet. This is a rare opportunity to show off the ternary operator. Let's pull the palette based on whatever fpal points to. Declare all that. Now we'll read the image data as we've always done. This time the loop has to account for the presence of a palette or not. If the file has a palette, then we should reduce the image size by 768 bytes, or else we'll run past the end of the loop. Remember, we can't start at 768 because we're using the current byte as an offset, so it has to start at 0. Now here's a fine point. We want to close both the palette file and the pic file, but we don't want to just throw both closes because most of the time fpal will be the same as fin. Closing the same file twice is probably undefined behavior on some systems, and I'm sure it's a seg fault on POSIX systems. Let's just check for that, just in case. Now everything else is the same, so let's speed through this part. Okay, let's build. Of course, nothing works the first time. Oh, I forgot the minus sign. I bet if I had a real IDE instead of Notepad++, I'd have caught this. Alright, let's build again. Good. Now let's process all the files. Awesome, we got them all. Wow, it even worked for number 19. I guess it really was 320 pixels wide. I'm not sure that's actually used in the game, though. We didn't see it in the exe file. So this time we used a disassembler to extract data about image files from the application binary. Now, otherwise, we would have been making a lot of guesses about the file dimensions. Some would have been difficult to guess, like file number 18 is 170 by 104. Now, I think we're almost done with the graphics assets. There's just the ships, game menus, and fonts left. Thanks for watching.